Hello Math 3A. Here's some examples for problem set number 6. In case you hadn't caught it before, my name is Greg Perkins. I'll be your host. Find all the subintervals where the function is increasing and decreasing. So increasing means that the derivative is positive. Decreasing means the derivative is negative. And it just so happens that the number that separates negatives from positives is 0. So the first thing we need to do is take the derivative and set it equal to 0. Also notice this is on the interval from 0 to 2 pi, so we may need to find more than one solution. But first, for the derivative. So this function got squared, so we actually need to start with the power rule. The derivative is going to be, bring the 2 down, multiply, and then subtract 1 from the exponent. And then the derivative of cosine. Well, the derivative of cosine is negative sine. And then set that equal to 0. I could even take this negative and put it in front. So we've got negative 2 times cosine of x times sine of x. The number negative 2 is never going to equal 0, but cosine can equal 0, and also sine can equal 0. So I like to just use the graph of cosine, which looks like this, from 0 to 2 pi, just like the direction said, 0 to 2 pi. And then where it equals 0 is where it crosses the x-axis, and this one is going to be pi over 2. And this one will be 3 pi over 2. Okay, so there's two critical values, pi over 2 and 3 pi over 2. And then what about for sine? So sine looks like this from 0 to 2 pi. And so there would be this, which is 0, this, which is in the middle of 0 and 2 pi, so that's pi. So I actually got three numbers, 0, pi, 2 pi, pi over 2, and 3 pi over 2. Now when is it increasing and when is it decreasing? So at this point, I like to take a look at the graph and make sure that you graph the original function, not the derivative. And let me adjust it. So cosine of x being squared. And I need to change the window to go from 0 to 2 pi. And cosine squared should range between 0 and 1. So the graph looks like this. It looks like a bouncing ball that keeps going up and down to the same heights. Okay, right there's 2 pi. So it should be that this is 0. In the middle would be pi. So this right here, that should be pi over 2. I want to test that. Trace and put in pi divided by 2. Yep, the cursor's right there. This is pi over 2. And then this one should be 3 pi over 2. So trace and test 3 pi over 2. And the cursor's right there. So this is 3 pi over 2. Okay, now, where is it increasing and decreasing? So for increasing, I'll put that answer right here. And then for decreasing, I'll put that answer right here. So increasing would be this part is going up, and this part is going up. So for increasing, the interval would be pi over 2 to pi, and then also 3 pi over 2 to 2 pi. So for increasing, that's pi over 2 to pi. And notice that these are round parentheses because at pi over 2, it gets to the bottom, which is where it's neither increasing or decreasing. So this needs to be a round parenthesis. And then also from 3 pi over 2 to 2 pi. And then put a union in between, and we're done with the increasing. Now decreasing would be this part in here, and then also this part in here. So decreasing would be from 0 to pi over 2, and then from pi to 3 pi over 2. Okay, let me just double check. I asked where is it increasing, where is it decreasing? So there's increasing, there's decreasing. And all right, that one's done. Now let's move on to part B, which is going to use the second derivative. And that's going to be where is it concave up and where is it concave down. So dealing with the same function. So concave up means that the second derivative is positive, and concave down means the second derivative is negative. And again, the part that separates those, the positives and the negatives, is when the second derivative equals 0. So the first thing we need to do is find out the second derivative and when does that equal 0. So if I go back to this page, I have the first derivative right here. Actually, I like it a little bit better with the negative 2 in front. So from the previous work, y prime equals negative 2 times cosine of x times sine of x. All right, now find the second derivative. Well, with the second derivative, I'm going to look at it like this. Like the negative 2 just gets factored out, and then take the derivative here using the product rule. So y double prime is going to look like a negative 2 got factored out. And now take the derivative of cosine, which is negative sine, and then leave the sine function alone. The product rule then says plus, and leave the cosine alone. And now take the derivative of sine, which is cosine. And then set that second derivative equal to 0. Well, this part right here, that's negative sine squared. And this part right here, that's cosine squared. And now we need to find out where the second derivative equals 0. So, well, a negative 2 is never going to equal 0, but this thing could equal 0. So 0 could equal negative sine squared plus cosine squared. And there's lots of different ways to proceed. You could say, well, cosine squared is equal to 1 minus sine squared. You could use trig identities. I think what I'm going to do is take this negative sine squared and move it to the left side, or in other words, add that to both sides so that it becomes a positive sine squared. And then I could divide both sides by cosine squared. Good time to use the red pen. And the reason for doing that, well, there's actually two reasons. One is that's going to simplify the right side because it's only going to equal 1. And on the left side, it's going to simplify because sine divided by cosine is tangent. And as long as they're both squared, that means it's going to be tangent squared. And then I could take the square root of both sides. Don't forget, when you take square root of both sides, then on the right side, it's actually going to be plus or minus the square root of 1, which equals 1. So then it's saying, when does tangent equal a plus or minus 1? So the tangent function looks like this. It's got an asymptote over here at pi over 2 and another asymptote over here at negative pi over 2. Then when does it equal 1? So if you use tangent inverse, So if I use tangent inverse of a 1, it says 0.785. That's actually pi over 4. So if I ask the calculator, divide that by pi and change that to a fraction, it's going to be 1/4. So that would be pi over 4. So pi divided by 4, sure enough, equals that 0.785. And for the tangent inverse of -1, I get the same thing, but with a negative. So that means that this answer right here would be pi over 4. And where it equals -1, it would go over here and say there's also an answer at negative pi over 4. Now, according to this, all of the answers are supposed to be positive. So negative pi over 4 isn't one of the answers, but what I can do is extend this graph out, draw another branch of the tangent function, and if you continue across, there's going to be another answer right here, and if you continue across, there's going to be another answer right here. So at first I got x equals pi over 4, and I also got x equals negative pi over 4. Since the tangent graph goes from negative pi over 2 to pi over 2, that's a length of pi. So when I drew this line right here, I was basically just adding on a pi. So this is probably one of the answers. Another answer would be if you take pi over 4 and add pi. Another answer would be if you take negative pi over 4 and add pi. So let's see, this would be 1/4 plus a whole is 1 1/4 or 5/4. And this would be a whole minus 1/4, which is 3/4. So let's see, I'm supposed to go all the way out to 2 pi. So this is only 1 1/4 pi's. So I think I still need to keep going. So I'll add another pi. So take 5 pi over 4 and add another pi. Take 3 pi over 4 and add another pi. So this would be 4 pi over 4 plus 5 pi over 4. That's 9 pi over 4. And that is actually bigger than 2 pi, so I actually don't need that answer. This one would be 4 pi over 4 plus 3 is going to be 7 pi over 4. So this is within the range, so that is one possibility. 3/4 of pi, that is within the possibility. This is negative, so that's not within our range. This is within the range, and this is within the range. So with all of that, I actually need another piece of paper. Okay. Can I fit it all on the screen? I think so. So if you look at the interval from 0 to 2 pi, because that's what the directions said, then the first one that I got is pi over 4. The next one would actually be 3/4 of pi. The next one would be 5 pi over 4. And then there would be 7 pi over 4. Okay, now I'm done with that. So now I need to figure out where it's concave up and where it's concave down. So basically I have 1, 2, 3, 4, 5 intervals to look at. And if we go back to the graph, and especially if I focus in on that. So if I put the first number, which was pi over 4, pi divided by 4, then I can quite obviously see that in here, this is concave up. And I'm pretty sure that if I put 3 pi over 4, it's going to be right there. Let me test that. 3 pi divided by 4. So this was pi over 4, and this is all concave up, and that's the 3 pi over 4. So this is concave up, and then this is concave down, so it's just going to alternate. And next would be 5 pi over 4. So right here, this middle part is concave down, and then this is concave up. And then this last part, since it's a trig function, actually alternates. So this would be concave down, and then concave up, concave down, concave up, concave down. All right, now I just need to label my answers. So for concave up, that would be the pi over 4 to 3 pi over 4. And the next one would be 5 pi over 4 to 7 pi over 4. And then for concave down, well, when I took the second derivative and set it equal to 0, I got these answers over here. And notice that 0 was not one of these answers. So that means that at 0, it is actually concave down there. So that one actually deserves a square bracket. If you go back to the graph, and I change the window a little bit, and I'll change it to like -1, just so we could see what's happening at 0. So right there at 0, as it's going through 0, this is concave down. So at 0, it's not changing concavity. So at 0, it is concave down. So this deserves a square bracket on the 0. And then to pi over 4, so that's this one. And now I need this one, which is 3 pi over 4 to 5 pi over 4. And then this last one is going to be 7 pi over 4 to 2 pi. And just like with the 0, that last one deserves a square bracket. Okay, then on to the last example. I think this is an interesting application of calculus. So there's an 8-foot wall. So let's say this is the wall, this is the ground, and it's standing 12 feet from a building. So this is an 8-foot wall. It's standing 12 feet away from a building. So this is going to be the building. Nice windows or something. Oh, looks more like a prison. Well, that could be sort of appropriate, because what's going to happen is someone's going to get a wooden beam, and they're going to go from the outside. They're going to have to be over a little bit farther. They're going to go from the outside. They're going to have that beam go over this wall so that they could break into the building. Or perhaps there's a cat that's stranded on the top and they want to save the cat. So this is the beam. And I need to find out how long that beam is. And of course, to save materials, use the shortest beam possible. Don't just go in there with like an 800-foot beam, because that would be really hard to do. Use the smallest one possible. Okay, so I need some information. Like right here, I don't know how far out this beam is going to go until it hits the ground. So I'm going to call that X. Also, I don't know how high up it's going to go on the building. So I'm going to call that Y. And then this is a right triangle, assuming that this building is standing upright, not like the Leaning Tower of Pisa or something. So this is a right triangle, which means I could use the Pythagorean Theorem. So b squared is equal to, now this side on the bottom is actually x plus 12. And then this leg is y, so that's going to be y squared. Now what I need to do is I need to find out what could I substitute for y. Also notice that this over here has nothing to do with the 8 so far. It's been ignoring the 8. So what I'll need to do is, I'm going to take the derivative of this later on, but first I need to find out what y equals. And it's probably not going to be a number, it's probably going to be something like 8 over x or something like that. So how do I do that? So I'll leave this part over here and I'll take the derivative later on. Now what I'm going to do is look at this little triangle right here. So if I take that out, it is a little right triangle where the bottom is x and then going up is 8. Now look at the whole right triangle. Along the bottom is x plus 12 and going up is y. So these are called similar triangles. And that means that I can set up a proportion. I can go y divided by 8 will equal x plus 12 divided by x. So y divided by 8 equals, so I have to be consistent, this divided by this equals this divided by this. So x plus 12 divided by x. And the whole goal here is I was trying to solve for y, so now just multiply both sides by 8. Okay, so that is what I substitute for y over here. So it's going to look like b squared is equal to x plus 12 squared, and then replace this with y. So that's going to be an 8 and then x plus 12 over x, and then all of that needs to be squared. So this is the function that we're going to need to take the derivative of and set it equal to 0. Although before doing that, I'm noticing that this has x plus 12 squared, and this also has x plus 12 squared. So I think I'm going to factor that out first. And I only know to do that because I've done this problem in the past, like right here. And right here, I didn't factor it out, and it was just getting longer and longer and longer. And I was like, wait, isn't there an easier way? Here's the easier way. So this has x plus 12 squared. I could factor that out. This has x plus 12 squared, so that got factored out. Then what remains? Well, since I factored this out, it's going to leave behind a 1 plus. And since this x plus 12 and the squared got factored out, what remains is the 8 over x, but still has to be squared. So on top, an 8 squared will be 64. On the bottom, it's an x squared. Okay, so that is what we need to take the derivative of. On this side, the derivative is going to be, first of all, the power rule, 2b, and then b prime. On the right side, I need to use the product rule, which I think it would be better if I get another piece of paper. So I'm going to transfer this over because I'm running out of room, and then take the derivative. So I have b squared equals the x plus 12 is squared, and then times 1 plus 64 over x squared. All right, so that's what I'm going to take the derivative of. You know what? Another thing that I could do right now is graph this, because I'm supposed to find the shortest beam. And if I set this upright, it should be a function that has a minimum. So I'm just going to graph this as if it were y equals. So it's an x plus 12 squared, and then 1 plus 64 divided by x squared. Okay, then look at that function. So for the window, so x is x is this distance. So if the numbers on there are like 12 feet and 8 feet, I think if I went from 0 to, I don't know, maybe 20 feet at the most. And then y, well, these are pretty big numbers because if you have 12 squared, that's already a big number. So I'm going to say y goes up to, I'm going to guess 150. And I just want to see, is this a graph that has a minimum? And I'm actually not seeing the graph. Oh, it's up there in the 700s. So actually I need to have this go, because of these squares, the numbers are pretty big. Okay, that's good news. So it is a function that has a minimum. So I think I'm on the right path. Okay, so take the derivative. Let me adjust the lighting. There we go. And now take the derivative. The derivative on the left side is going to be 2 times b, and then, because of the chain rule, times b prime. On the right side, I need to use the product rule. So that's going to be, the derivative of the first one is 2 times x plus 12, and then subtract 1 from the exponent. That's the derivative for the first one. And then just copy down the next one. Okay, there's half of the product rule. Now copy down the first one, x plus 12 is squared. And now take the derivative of this one. Well, the derivative of a 1 is 0, and the derivative for, if you have x to the negative 2, so this is basically like x to the negative 2, and you take its derivative, that'll be negative 2 times x to the negative 3. So the 64 can stay there, and then when I take the derivative, I'll have an extra negative 2 times that. So that would be negative 128. And then instead of writing x to the negative 3, I would write it as over x cubed. Okay, now set the derivative equal to 0, which means this side is going to be 2 times b times 0, so that means it's 0. And I can do some algebra, like x plus 12 shows up in both places, so I can factor out x plus 12. And I actually don't see anything else I could factor out. Okay, so if I factor this out, there's still going to be the 2 times this. So that means there would be 2 times 1. And there would also be the 2 times the 64. So that's going to be a 128 over x squared. Now moving on to this part. So I factored one of these x plus 12s out, but there still is one that remains. So that means I need to do x times this, in which case when I multiply x with this, it's going to cancel one of these x's. It's going to leave negative 128 over x squared. And then there's also a 12 that remains, so I have to put 12 times a negative 128. So positive times a negative. I know it's going to be negative, and I know that it's going to be over x cubed. And then a 12 times a 128. 12 times 128 is 1536. All right, almost done. So if you set this one equal to 0, that's going to give you that x equals a negative 12. Well, for one thing, we can't have a negative length. And also, if x equals negative 12, that means that this point got moved over to here, which means somebody must have torn down this wall, and that is not possible. So this is not going to give us any solution. The solution must come from this. And then if you look at this, the good news is this negative 128 over x squared and positive 128 over x squared cancel each other out. So all that's left is 0 equals 2, and then minus the 1536 over x cubed. So by doing that factoring, it definitely simplified the problem. I would then take this negative term and move it to the left side. It will become a positive 1536 over x cubed, and then equals 2. Next, you could multiply both sides by x cubed, so the right side is going to become 2x cubed equals 1536. And then divide by 2, and I'll just do that off camera. 1536 divided by 2 is 768. So that will eliminate this 2. And finally, take the cube root. So x is equal to the cube root, so math cube root of 768. So 9.158 feet. 9.158 is what x equals. Now, the only small problem is that's not the answer to the question, because what I just found is basically when they put the beam, how far out is it going to be from this little wall? It's going to be 9.158 feet. So that's this x right here. So I still need to solve for b. And so I could use this one that I circled, or in other words, this one that I circled, and substitute the x, and then find out what b equals. So I need to substitute x in here, and this is the x that I need to substitute. So to save some typing, what I'm going to do is, down here on the bottom of the calculator, store that answer as x. So now anytime I use an x, it's going to plug in a 9.158. So then I'll plug it in here. So an x plus 12, that gets squared, and then times a 1 plus 64 divided by x squared. So I'm just using this right here with the x's. And it turns out to be a 789, but keep in mind that's what b squared equals. So to finish this up, b squared is equal to a 789.269. And then just take the square root of that 789. So second, the square root of 789.269. And that beam would actually need to be pretty long, 28.094 feet. Being that long, it should probably be a steel I-beam so that it doesn't bend or break. All right, so that's it. I'll see you next time.